So any idea how voltage is defined? I gave you some understanding, right? Analogical understanding.
No charge through a certain voltage.
On voltage? How is voltage defined? What is voltage? V is the unit, right? What is the base unit of voltage? Any idea? Volt? Volt is again a scientist name, volta. Okay, any unit you take, most of them are scientist name. Weber, voltage, volta, ampere, coulomb, ohm, anything else? Watt, joule, Newton, anything else you know? All these things are scientist name. Tesla, right? Hertz, anything else? That's all. So all these things are scientist names, okay? So, but when I say base unit, right? So it's something like, what is the base unit of Newton? Kg? Kg? Newton is F is equal to MA. For mass it is kg. Acceleration is? Meter per second square. That's all. That is your base unit. So Newton is kg meter per second squared. Okay, that's a base unit. So similarly, for volt, right, I would say it's nothing but joule per coulomb. Okay, again, joule is not the base unit. Joule can be written as Newton into meter. Newton can be written as kg meter per second square. So it just keeps on going, right? But for now, for our understanding, I think we can stop here, even though this is not a base unit. So you should understand voltage is joule per coulomb. Okay. What it means is, the way voltage is defined is, so if I had a plus Q charge here, right? And if I am pushing some kind of plus test charge, right, 1 coulomb, right? If I am pushing it from the infinity, right? So will this plus and plus, will it attract each other? No, right? Which means if at all I want to bring this plus closer to this, what should I do? I have to do some work, right? I have to do some pushing. So which means I have to push it from the infinity.
So 1 joule of work move a test charge Q from infinity to a point.
Yeah. So yeah, that's the definition. So basically, so how much work is done to push this 1 coulomb to a given point R from infinity. So this is at infinity. So from infinity, you are pushing some 1 coulomb charge or test charge. So how much work I have to do? That work done is called voltage. Okay. So it's a little bit, confusing definition, but that's the way it is defined. So work done per coulomb of charge from infinity to a point at R. Is called voltage. So now does this make sense? Joule per coulomb. So how much work you are doing to push 1 coulomb per coulomb, right? So this is the definition of voltage. So we have a small derivation. Again, we will be getting into integration, right? So I hope you folks are a little bit, comfortable with the integration because we did some integration in the previous chapter, right? So what I'm going to do here is, let's say I have to push it something like, so I'm going to take this distance as x. Now let me draw it as a separate diagram. So this is for the definition, right? So let's say at a given point of x, right? So how much work I have to do? So that's your, how much push I have to give. So carefully listen. So suppose if I have something pushing here, right? So will the force of pushing here will be more, or when it comes here it will be more? Which one will be more force? It will be here. Why? What law? Coulomb's law, right? R squared, 1 by R squared, right? So that means closer the distance, force will be more. Makes sense? Whereas the distance here is more, which means the force will also be less. Which means at every point the force is not constant, the force keeps changing. As they come closer and closer, I have to do more hard work to push it, right? So that means, what is work done? Work done is equal to force into displacement, right? So if I say a small amount of work done is given by work done force into small amount of displacement, ds or dx, we take this dx. Okay, a small amount of work is done by pushing, giving force F for a distance of dx, right? So if you understand this, after this it's easy. So if I want the total work, what should I do? Integral of dw, integral of f dot dx. But f, is it constant or is it changing? It's changing with respect to distance. So what is the formula which connects force and distance? No, I am talking about the force due to these charges. Coulomb's law, right? So that means F can be written as K Q1 Q2 by R squared, but I said this is distance x, so I'm going to say x squared dx. Okay. Later on in integration, you'll be studying in your mathematics that whenever you have integral of y dx, y should be written in terms of f of x. So dx, f is written in terms of x. Is the q changing? No. Constant? Not changing. So k, q1, q2 is constant. So I can take k, q1, q2 as constant, dx by x squared. Maybe here take this down as this is q1, this is q2, some charge, how much work I am doing. This is q1. Okay. How to integrate 1 by x squared? Anybody remember the formula?
1 by x power.
We did something like x power n dx is equal to x power n plus 1 divided by n plus 1. Okay, don't worry about the c right now, but this will be taken as x power minus 2 dot dx. This is constant. Can you apply the formula? X power minus 2 plus 1 divided by minus 1.
X power minus 1.
But where are you pushing? You are pushing it from infinity to which point is this? X, right? From infinity you are pushing it to X, right? So, but let's say I want to have it at a given point. X is a variable, but if I want to have the potential at a given point of R. So what I am trying to say here is X is a variable. R is a given point. R is something like a number. X is variable. It can be anything. R is something like, okay, 5 meters, 10 meters, like that. Is it making sense? So I am pushing it from infinity to R. So that means I am going to say it's pushed from infinity to R. Infinity to R. So in limits, what should I do? Should put infinity to R. Okay. Which means this can be written as K Q1 Q2. This is x power minus 1 minus, so the minus comes here. So minus x power minus 1 infinity to R. What is x power minus 1? 1 by x, right? So what can you say about here? Upper limit minus lower limit. So 1 by R minus 1 by infinity. What is 1 by infinity? 0. So it will be K Q1 Q2 by R. So I made a small mistake here. So the force which you are pushing, is it this way or this way? You are pushing it this way. But the Coulomb's force is this way. Repulsion is this way, right? So the force is this way, which means you are giving a force opposite to the Coulomb's force. Do you agree? So that means here you should put a minus F dx. So it will be minus here. So all along you will have a minus. So when this minus and minus combines, it will become plus. So minus and minus, it becomes plus. So make a note here. Force is given against the repulsive force given by Coulomb's law. So it is negative. Is this making sense? Anybody having any issues? The repulsion force is this way according to Coulomb's law, but the force which you are doing work is this way, which means you are giving a force opposite to it. So that means work done is this way. K Q1 Q2 by. You have negative here, but then what happens to this negative? It becomes plus. Okay, come back to this. Work done per coulomb. So what does that mean? Voltage V is nothing but W by Q. Do you agree? Work done per coulomb. Is that correct? Is this similar to something else which you have studied? Per coulomb something? Per kg apple, per kg orange? Electric field, right? So I told you electric field is E is equal to F by Q. Force per unit charge. This is work done per unit charge is nothing but voltage. Okay? So voltage is nothing but work done per unit charge. So I said this is work done. So if I want V, what should I do? W by Q. So W by, so K Q1 Q2 by R squared divided by, I have to divide by the charge which you're, R, you're right, yeah. It's only R. So I have to divide by the Q. So which Q should I take? I should take Q2. Q1 is the main charge. This is the test charge. So I have to divide by this charge. So I said the final answer is better write it as 1 by 4 pi epsilon naught. K is nothing but okay.